So I just bought this book on commutative algebra, and I thought I'd prove one of the most important and also basic theorems of ring theory, which states that ideals in A mod G correspond one-to-one with ideals in A that contain G. So let's look at what's going on before we get to the algebra. I visualize the ring A here, where B is a subideal and G is an ideal that is contained within B, and obviously 0 is contained within everything. And so what happens under this morphism, right, we send A to A mod G, we quotient out the G, so that G is going to be reduced to a 0. So this is what our target ring is going to look like. A mod G contains the ideal B mod G, and G gets sent to 0. So if we want to identify ideals with each other, well, this direction is pretty obvious. You just take an ideal here and you put it under the morphism and you get an ideal there. However, going back, we have to actually prove that. So we already have kind of a hint. We just look at the pre-image and we prove that that is an ideal that contains G. So recall that the pre-image is just the collection, the set of elements in A that gets sent to B mod G here. So we have to prove that it's an ideal. That's fairly easy to do because the addition here gets ported to the addition there, and since that is an abelian group, this is also going to be an abelian group. And we can see that the same holds for multiplication by any ring element. It's just going to be ported to any ring element from A mod G onto this ideal B mod G. So this is an ideal. Why does it contain G? Well, because G gets the 0, so we can just throw it in there, because it gets mapped to 0 anyway, and every ideal contains 0. So we've shown that the pre-image of an ideal here is an ideal there, which contains G. And so we can identify ideals here with ideals there with ideals there, and so we've proven our theorem.